Okay, so we switched rooms for those who are in person. Had kind of a small enough number where I think if you want, you can show up every single day, Monday, Wednesday, Friday. For those of you, if you're watching, you weren't able to come, but you're on the list, it's in WB 136. I thought the room number was right and I was correct. Also, I think I've got like a whiteboard behind me, so I'm going to try to use this a little bit more as opposed to the one that I was just kind of bringing, since it's all kind of on the kind of set up a little bit nicer. I don't know why I wasn't given this room originally, but you know, with having a few more seats in here, it allows us to get every single person in here if they want to be every day. Okay. All right. So I posted kind of an additional video this weekend. It was basically just more Bayes theorem examples. So I went through 2 different examples. If you were having some trouble with that last class, take a look at that. It just gives you another couple looks at it, because that will be some question you can expect to see on the exam. I got the practice exams up there. So if you take a look on Canvas, and I'll actually X out of this, and we'll go to Canvas real quick. You go to Files. There should be a folder that says Exam 1 Practice Materials. You've got a practice exam with its answers, another practice exam with its answers, and then kind of the formula sheet that typically, if we took it in person, you kind of hand these out. Once you go to take the exam, you'll be able to kind of have these open and use these formula sheets, so it has everything kind of all in one place for you. You don't have to worry about creating your own or anything like that. Everything you should need, every formula you should need should be somewhere on this formula sheet, okay? I'm expecting that probably today, Wednesday, we'll go through the material. Friday, we'll probably have a little bit of materials to kind of cover. It'll be stuff we've already talked about, just some more examples. And then I'll probably start working through some of the practice exam problems. So we'll work through a few practice exam problems Friday. We'll do another kind of like little review session on next Monday, which will be the day that you can take the exam. But if you want to kind of have some last minute study, I'll use in-class time to do another, like go over some of those practice exam problems, okay? That second Excel assignment is due at the end of the week on Friday, by the end of the day. So if I would suggest starting on that as soon as possible. If you have any questions with that, email me, set up some Zoom meetings, or you can email your file. If you're like stuck on something, I can try to kind of help you work through it that way, okay? Any other questions for me before we get started? Okay, all right, so we're gonna start talking about eventually getting us to a point where we're looking at real continuous distributions. But to get to that point, we're going to first start out talking about not continuous distributions, but discrete. All right, so we have these things called random variables. It's really just an experiment that's being run, and we don't know what the outcome is. And when I say experiment, this could be something going all the way back to rolling a die. Right? So I roll a dice, can I get a 1, 2, 3, 4, 5, or 6? Each outcome has a different probability of occurring. It's just we'll be talking about some very specific discrete random variables, right? So I'll go over this kind of quickly because it's things we've already talked about, right? So this random variable, we don't know what the outcome is going to be, but it could be discrete or it could be continuous, right? Continuous, we'll wait until after the first exam to talk about those. So the only kind of discrete, or the only random variables we're focusing on prior to this exam are discrete random variables. Okay? So we're going to use this capital letter X just to represent what this random variable is. And we'll see how that kind of plays out here in a second. Every single time we run this experiment, right, we're going to have different outcomes that we can record. So even if this is simple as rolling a dice, I roll it, I record what I see on the first roll. I roll it again, I record what I see on the second roll, so on and so forth. Okay, so these discrete random variables, it's like we've talked about before. It's usually a small number of responses, or typically, when I say small number of responses, it's a small number of integers, right? You can see a 1, a 2, a 3. Now, it doesn't necessarily have to be that. It could just be a small number of responses. So maybe I could see a 1.5, a 3.5, a 4.3, and a 2.9. Those are the only outcomes I can see. But it's a very small set, and there's only like 4 possible outcomes that it could be. So usually, it's an integer, but it could just be a small subset. Usually, I think every example I'll give you is just going to be integers, right? So that'll kind of keep it simple. So we've done this before. Think about a number line. If it's discrete, it can be any one of these integer values, but not something in between, right? For the sake of this example, or for the sake of this class, we're going to keep it as kind of integers. And then continuous, I won't waste time on this because we're going to review it anyways. Later on, we'll look at variables where it can take on any value, but that's kind of after the example, right? So these are just slides we've already looked at. Kind of talked about what are some different possible variables we could think about that are discrete. Well, what's the number of dependents on our reported tax return? Right, you could see 0, 1, 2, 3, 4, 5. I don't know how high up we would go there, but it'd be integer values, and it would be somewhat a small set of possible values we could see. What is the distance that you are from, I don't know, the nearest store? Well, this could be continuous, right? Because I could break this down to, I'm 4.31 miles, right? I could actually have a very large array of possible outcomes for that. And then kind of the last one, thinking about, you could ask even a survey question. Do you own a pet, cat or a dog? 1, if no pet. 2 would represent only a dog. 3, only a cat. 4, both. Right? So sometimes we'll almost see like this really, you can think about almost like a qualitative variable, but we've coded it in a way so that it is now a discrete variable. So we'll look at a couple different examples. There's a few just to kind of set us up. Like I said, we've talked about these a little bit before, kind of the difference between discrete and continuous. So once we know we're dealing with this discrete random variable, it has these different outcomes that we could see, but not all of them are equally as likely, right? Not every, think about family size, right? The number of dependents. Seeing a 1 or a 2 is probably way more likely than seeing an 8 or a 9, right? And so there's going to be different probabilities associated with seeing every different possible outcome. So what this probability distribution is going to do is it's basically just going to kind of show us each possible outcome for X, what's the likelihood that we see that outcome occur, right? And usually we can show that in a graph or a table to kind of give a nice visual to it, but it could just be a function, right? This function is going to tell us what's the probability we see a 0, what's the probability we see a 1, what's the probability we see a 2, what's the probability we see a 3, right? Now for these discrete random variables, initially, this probability distribution isn't going to be like a nice, well-behaved function. It's just going to tell us what the probability of 1, 2, and 3 are. And we'll kind of see this here in just a second. So the way that we're going to denote this probability mass function is just the probability that we see this random variable X take on a specific value. Right? So what's the probability that this random variable X takes on the very first outcome? Right? So here, this lowercase x, this is all the possible outcomes we could see. So you might think about it as, where are my markers at? Here we go. So I could just have, here's my X values, right? All my possible X values. And then I would have kind of their counterpart. This is my probability mass function, which just tells me the probability I see a 0 is 0.2, probability I see a 1 is 0.3, this is 0.4, what? Seeing a 3 would be 0.1, right? So I would have a bunch of different outcomes and their associated probabilities, right? So this P is probability that X is equal to some specific outcome. This lowercase x take on 0, 1, 2, or 3. So if you think about it this way, we now have like X, Y pairs. We could really just plot these just like we did frequency distributions, right? Once I have kind of the different outcomes, I have these different outcomes. Well, the first one has a probability of 0.2, 0.3, 0.4, 0.1, right? It's really things that we've already done, right? It's just now, it's kind of like, it's an uncertain outcome. We haven't observed it yet, but we know the probability that we see the different outcomes, okay? So it doesn't look a whole lot different than what we've necessarily done once we had like our relative frequencies and the different bins, but now our bins are not bins because we have a discrete variable. They're just integer values, okay? So, just like any other probability, these probabilities have to be somewhere between 0 and 1, right? Let's say, for instance, I put a 4 right here, right? What's the probability I see a 4 occur? Well, these are already add up to 1. It could be that the probability I see a 4 occur is 0, right? That's the lowest it could be, right? Now, the highest it could be, which would be a pretty uninteresting example, but if I had one outcome and the probability that it always occurred, then the highest the probability could be is 1, right? Now, we won't see examples like that because that's not really a random variable, right? It's not random if it's always the same value, right? But we could see it range anywhere from 0 to 1. And then very similar to relative frequencies, well, if we think about if I have every single possible outcome, if I add up the probabilities of each one of those outcomes, I've kind of covered every single possible scenario I could see, and so those probabilities should add up to 1. Just like with relative frequencies, right? We're adding up the probabilities of seeing every different possible outcome. Once we've covered every possible outcome, those have to add up to 1. So like I said, this is kind of similar to things that we've talked about in the past, just look at slightly different spin on it. Any questions on that before we keep moving? Shouldn't be too bad yet, I don't think. I don't have it, so I'll pull the chat poll. All right. We could also do a cumulative mass function, and this is similar to the idea that we did with relative frequencies when we made cumulative relative frequencies. Essentially, what we'd be doing there is saying, what's the probability that x is less than or equal to 0? Well, for the first category, that's really easy, right? It's just whatever that probability is. But then when we say, what's the probability it's less than or equal to 1? Well, that would be the probability it's equal to 1 plus the probability it's equal to 0. Right? Now, we could, if we wanted to, graph that. And then what's the probability x is less than or equal to 2? Would be the probability it's equal to 2 plus the probability it's equal to 1 plus the probability it's equal to 0. And what's the probability it's equal to 3? Sorry, not equal to. Less than or equal to 3, it would be the probability it's equal to 3 plus 2 plus 1 plus 0. Right? So this idea of cumulative, it's the same thing we were doing with relative frequencies, right? So instead of exactly being equal to one value, we want the probability that it's less than or equal to that value, right? Just kind of like a cumulative GPA. You're not just looking at the GPA for this semester, you're looking at the GPA for this semester plus every semester before. Right? So as we get to the higher values, as we get to higher x values, our cumulative frequency should be getting closer and closer to 1, right? If these are the only possible outcomes I can see, once I get to, not even 4 here, once I get to 3, well, I'm already up to that probability of 1 because there's no other outcome I can see past 3. So if you're telling me that the highest this variable can go is 3, well, then the probability I see a 3 or anything below it, well, that's just 1, right? So as we get to higher values, this cumulative frequency approaches 1. And as we get closer to those lower values, right, we have a kind of lower cumulative frequency because there's no values below it. So this is the idea of our cumulative mass function. So we'll go through kind of an example with a little data set, and it's going to look almost identical to what we did with relative frequencies. So I have the unfortunate task of, I guess, I don't know, I chose it, so it's not a task, but of being a Purdue football fan. So I grabbed a bunch of their kind of data on the number of wins per season. I then counted up the number of seasons they had 0 wins, number of seasons they had 1 win, et cetera, et cetera. Right? Well, I now have frequencies, right? I have different possible outcomes. I know that if they were playing this year, let's say next year, that I would see them either win 0, 1, 2, 3, 4, all the way up to 12. One of these is going to be the outcome, right? Now, they all have different likelihoods of occurring. The likelihood they win all 12 games is probably relatively low, but hopefully also the probability they win 0 games is low as well, right? Well, using these frequencies, I can figure out what my probabilities are, almost just like we were doing last week when we built our own contingency table, right? We first have to find the frequencies. We can then convert those into probabilities by simply dividing by the total number of observations. So if I have my total number of observations here as 35, it's pretty easy to get my probabilities, right? By just dividing each frequency by the total number of observations. And now I've got essentially this discrete random variable where I have every single possible outcome and the probability of seeing each one of those different possible outcomes. Now notice here I gave you an example where the probability for some outcomes could be 0. Right? We said it could be equal to 0 or higher, and then it could be less than or equal to 1. We don't have anything that's equal to 1 here. So I now have these different XY pairs. I could graph this if I wanted to. So I could throw this into a probability distribution, right? Just with all my different possible outcomes and use those probabilities as my y-axis, right? That's what I did up here on the board, just with an example that didn't have any context to it. So this is, this is almost exactly what we did with relative frequencies, right? Literally, if once we were doing it in Excel, it would look no different, right? It's just now we know we're not dealing with bins, we're dealing with just discrete values, and we have a smaller set of them, okay? So this is pretty easy, and this, this starts to give us an idea about what the distribution of wins looks like, right? You can kind of imagine if I have a higher number of possible outcomes, I start to get more of these rectangles. It starts to look more and more like a continuous distribution. But for right now, it still looks pretty discrete. Having a graph is nice, kind of tells us what the most likely outcomes are. some of the outcomes that aren't as likely. It's really, like I said, this is almost like review, right? We've done stuff like this before, okay? So if we have this discrete random variable, how do we then find the mean, right? So it's not going to be just as easy as finding a mean with, say, a data set with 10 numbers, because when we think about here, we've got I wouldn't just add up 0 plus 1 plus 2, 3, add up all these and then divide by the number of numbers I added up. Like that's kind of how we would typically do a mean. Because each one of these different outcomes, right, has a different likelihood of occurring. So if some outcomes are more likely to occur, what does that start to sound like? Something that we've already done. We've got a bunch of different possible outcomes, or we have a bunch of different numbers we want to find the mean of, but we know that some of those values are more likely to occur or happen more often or represent a larger number of people. That was where we couldn't just do a regular mean, we had to do a So it doesn't matter. So it doesn't matter if we don't want to think about population samples here because we're now just dealing with a discrete random variable, right? But if we're looking at kind of calculating a mean, and we know that different outcomes are likely to occur, yeah, we want to use a weighted mean, right? Because this value is way more likely, so we want to weight it more than values that, I wouldn't even say less likely here, right? That's impossible, or not impossible, but the probability is that this occurs as 0, right? So when we want to calculate a mean, we'll sometimes call this, what's the expected value, right? Because it hasn't happened yet, right? But based off the probabilities, we can figure out what the expected value is, right? So the mean of this discrete random variable, the equation's going to look something like this. Now, it should look really similar to what we did with weighted means, because we're going to take every single possible outcome for the variable x we're interested in, and we're going to multiply it by a weight. And then once we do that for every single possible outcome, we'll add them all up. Well, here, the only difference is our weights are going to be probabilities, right? So usually with a weighted mean, we also then had to divide by the sum of our weights. But what should the sum of these probabilities be? If we look across every single possible outcome, we add up those probabilities, that just adds up to, I said it earlier, 1, right? We add up the probability for every possible outcome, it just adds up to 1. So you could write a denominator in here if you wanted to. It would be the sum of all the probabilities. But because it's always 1, dividing by 1 doesn't change anything. We can essentially ignore that, right? So it's kind of like this weighted mean formula. But now these weights, we have some function for them. The function is just this probability mass function where it gives us the probability that x is equal to that specific x value. And now the sum of these weights, right, will always be 1. If we go back here, we said that, where was it? Right here, right? The sum of the weights will always be 1. So it's almost like weighted mean without the denominator. So it's almost like easier. I mean, I think it is easier, right? It's one less step, right? So it's the same procedure. We'll go through, take every single possible outcome for x, multiply it by its probability of occurring, and then add them all up, right? And that just gives us our mean of a discrete random variable. So it's not technically a weighted mean because these aren't, we're dealing with kind of expectations now, the probability that something occurs, not things that have already occurred and represent, a higher frequency of people or something like that. But it's the same kind of concept, right? To kind of related things we already talked about, it makes it a little bit easier. So, go here. There we go. So if I have all this data, how would I find kind of the mean of this discrete random variable? Well, I would go through, take the first possible outcome, 0, multiply by the probability it occurs, 0, add to that the next outcome of 1 times its probability of occurring, 0.06, add to that the next outcome of 2 times its probability of occurring, 0.03, and I essentially just do this for every single possible outcome. Right? Once I've done that, remember, I no longer have a denominator, right? The denominator is just 1, and so now I'm done. Once I go through, take each outcome, multiply it by the probability that it occurs, add them all up, that should give me the mean of that discrete random variable. So if I do that here, I'll get about 5.14, which kind of makes sense. If I look at these outcomes, which ones are the most likely to occur? 3, 4, 5, 7. So I'm kind of thinking about those are going to be the values that influence that mean of the discrete random variable the most. So I know I'm probably going to be somewhere in between 3 and 7. Sure enough, I'm almost smack dab in the middle, right a little bit, a little bit higher than 5. And that's probably because this 8 and 9 have a relatively high probability of occurring as well. So they'll pull up on the mean a little bit more than these outcomes of 1 and 2, which are a little less likely. So it's really combining what we've done, things we've kind of already done in the past, the ideas of a weighted mean. Just now we've introduced the idea that it's an unexpected outcome. We don't know what it is, and so we'll be dealing with probabilities, right, as opposed to weights. Okay? Any questions on that before we keep moving here? Like I said, I think this is, it's kind of review, kind of similar to things we've already talked about. You good with that? Okay. So the next thing we'll talk about, if we can do the mean of a discrete random variable, we can probably also do the variance, right? Once again, the variance is going to look almost identical to what we were doing when we did a weighted variance. It's just now we'll take each outcome, we'll subtract the mean, and here the notation looks a little different because this is just saying this is the mean of the discrete random variable, right? Not these numbers. It's not a data set. It's an actual kind of probability mass function that's giving us these probabilities that we calculate the expected value or the mean of this discrete random variable. So we'll take each outcome, subtract the mean, square it, and then just like before, instead of multiplying it by the weights, we'll now multiply it by the probability that that outcome occurred. Okay? So we'll do that for every single possible outcome x. We'll add them all up. Once again, we don't have a denominator because the denominator would just be divided by the sum of the probabilities, but the sum of the probabilities should just be 1. Right? So once again, it's like the weighted variance, but a little bit easier. Also, same rules apply. If I have the variance, how do I get the standard deviation? I would just be taking the square root. Right? So to go from the variance to the standard deviation, we just take the square root of that variance, just one more step. All right? So if we're looking at this guy here, kind of actually I should have had an animation set here so that this wasn't showing up. So here, we'll cover this up right now. So if I wanted to find the variance, I'm going to use that formula. So I'm going to go through every single possible outcome, subtract the mean, square it, multiply it by the probability it occurs. Now, I didn't write a separate column here. If you wanted to, I think that would be a good way to do this, where I go, okay, here's the first outcome, 0. I'll subtract that mean, which last couple of slides we found was 5.14. So we'll take that first outcome, 0, subtract that mean of 5.14, square it, and then multiply it by the probability that we saw 0. So just multiply it by 0, write that number down. Now for that first observation, it's going to be easy because if I multiply anything by 0, it's just 0. Then I would go to the next outcome. Take the outcome of 1, subtract 5.14, square it, then multiply it by the probability I saw 1, which is 0.06, write that number down. I could do that for every single observation, and then when I'm done, add them all up. Right? So that's kind of how I could do the intermediate steps, and I could do it that way. Or if I wanted to write it all on one line, right, it would look something like this. Right? 0 minus the mean squared times the probability 0 occurs, plus 1 minus the mean squared times the probability 1 occurs, plus 2 minus the mean squared times the probability 2 occurs, and then continue to do that all the way down to the very last possible outcome. So it's, like I said, the procedure is identical to what we did with the weighted variance. It's just now we've got probabilities as our weights. Okay? If we do that, we get about 5.38. There's no real necessarily meaningful significance to that value. It ends up being close to the mean. It's just a happy coincidence. Your variance could be 400 when your mean's 5. It just depends on the example. Okay? Any questions on this? Like I said, I'll probably go through this a little bit quicker than I usually would just because it's all stuff that we've really seen something similar to. Okay? So hopefully we're starting to get comfortable calculating these variances and just kind of the process. We'll work through another couple examples here. I'm just going to get, oh, we don't need to see this picture right now. So I'll do a little bit of board work here. So let's say I had this example where I've got 4 possible outcomes. So this is one where I said, it doesn't have to necessarily always be kind of as nice and neat as like it always goes up by 1. So here we have an example where we've got different bonus amounts that we could see. So 0, 3 million, 6 million, 10 million, right? And the probability we see each one of those bonus amounts given to this person, you know, is kind of right next to what the outcome is, right? So this is essentially our probability mass function. It's telling us the probability that this random variable, which represents the bonus amount, takes on 10 million is 0.15. The probability is 6 million is 0.25, so on and so forth. Okay? So if I wanted to find the mean here, all I'm going to do, I'm going to make this big so I don't have to keep switching. I can leave these numbers up. I'm going to go through every possible outcome, multiply it by the probability occurs, and then add them up. So all I would do here is 10 million. The probability occurs is 0.15. Add to that, 6 million times the probability occurs is what? 0.25. Add to that, the next outcome of 3 million times the probability occurs, which is 0.4. And then the final outcome could be 0. The probability occurs is 0.2. So all I'm doing is multiplying each outcome by the probability occurs and then adding them all up. Right? Now, if I just look at this before I even go to my calculator or however I'm doing this in my head, if I look at the different outcomes, I could see anything between 0 and 10. So remember, we're still finding a mean. So where does this mean or this expected value for this discrete random variable have to be between? Well, it has to be somewhere between the lowest and highest possible value. So we know it's going to be somewhere between 0 and 10 million. Right? Now, if I look at the outcomes that are most likely to occur, it looks like 3 and 6 are the most likely. Right? So we know that those are going to influence that mean the most. So my guess would be that if we're looking for the mean here, it's probably going to be somewhere between 3 and 6. Right? Because this 10 and 0 don't pull on it much either direction. These are going to be the ones that kind of have the higher weights associated with them. And so if I'm just guessing here, I'm thinking it's somewhere between 3 and 6. I can't say exactly, just looking at these values in my head, which way it's going to be. Probably a little closer to 3 because there's a 0.4 instead of a 0.25. So if I look at this, A and B don't really make a lot of sense. What would have to be true for A and B to be my mean is that the outcome of 0 would have to be like very likely to occur, right? Like a 0.8 probability or something. So that it would pull that mean a lot closer to 0, right? But it's not. So A and B seem like unlikely answers. So if I'm just trying to limit this down and guess, I'm probably going to guess C or D here. But to guess between those two, I probably have to actually just do the math, right? So if I do this out, I get what? 1.5 plus 1.5 is 3 million, plus 1.2 is 4.2, plus 0, so I get 4.2 million. If you enter this in your calculator, we should be getting that 4.2 is our mean. Okay? Any questions on that one? And I know this is small in person up here. Hopefully you guys can kind of see this okay. If I ever am like in the way, just let me know. Tell me to move over, okay? So I've got this mean of 4.2. How would I then find the variance? Well, first of all, I'm finding the variance. So which of these can I rule out right away? Which of these answers should I be able to rule out right away from finding a variance? What's the lowest a variance can be? 0, right? We said if we had a data set that had all the same value, that would be a variance of 0. Here, to have a variance of 0, what will we have to have? Well, we'd actually have to have a variable that had one outcome and the probability that occurred is 1, right? It's the only value we could ever see. So the lowest we could see is 0. We're never going to have an example where we have a variance of 0 because that's a boring example, right? And so we know that it's going to have to be positive, right? Because we square those deviations and probabilities can never be negative. So we automatically know that this variance has to be a positive value. We could rule out B right away, right? Can't be a negative value. From there, I don't know. I can't really pick and choose just looking at the numbers. And so I'm going to actually just have to do the math, right? So if I want to find the variance, I'm going to have to go through, take each outcome, subtract the mean, square that deviation from the mean, and then multiply it by the probability it occurs. So if I'm doing that here, what does that look like if I'm writing it out? All right, so we've got what? The first outcome is 10. The mean was 4.2. We'll square that value. And then the probability we saw at 10 was at 1.5 or 0.15. I would then add to that the next outcome of 6 minus that mean 4.2 times the probability that I saw 6 occur. Right? I'm just grabbing these numbers from this table. And then 3 minus the mean times the probability I see a 3 occur. And then 0 minus the mean times, what was it, 0.2? The probability that is a 0 occurs. Right? So I'm just going through each line. Like I said, you could calculate these, write the numbers down and do the intermediate steps, or you can kind of enter this in the calculator all at one time. Okay? Any questions on that before we keep moving? Okay with that? Hopefully this is looking like stuff that we've, similar to stuff that we've already done. Okay? All right, so I'm gonna make myself a lot smaller. Go down here. So I use these memes here, or these pictures, not memes. This is like a really good movie, just as a kind of a side. It's called The Big Short, and like if you're in a business college, I would suggest you watch this. It's about kind of the recession back in 08, kind of what led to it, kind of explaining mortgage-backed bonds. They do it in kind of a fun way. I always tell people, you guys are in the business college, so hopefully you probably understand this movie a little bit more than maybe the average person. My sister, who's like the biggest, like, I don't know, hippie, like bohemian person ever, even enjoyed this movie. And like, she has no idea what like a derivative is, or like she had no financial terms in her, language or in her vocabulary. So it's a really good movie. If you haven't seen it, I would highly suggest watching it. Also, just kind of a fun way to understand what happened with the financial crisis a little bit more. Okay. All right. So where are we at in time? All right. Yeah, we'll go through a little bit more. So I'll introduce this specific discrete random variable today, and we'll continue to do some work on it next class. I don't think we'll get through all of it today. So there's a very specific type of discrete random variable called a binomial distribution. Okay? So this binomial distribution, in order for us to have an example that kind of fits its definition, would be if we run an experiment, the same experiment over and over n number of times. This could be as simple as flipping a coin, right? I either see a 0 or a 1, heads or tails. But I run this experiment, say 50 times, okay? If I flip a coin 50 times, right, I can then start to think about, well, each outcome is either a 0 or 1, right? Each time I flip the coin. But out of those 50 trials, right, n is kind of the number of times I run the experiment, or we call it the number of trials. I could see 25 of those come up heads. I could see 30 of them come up heads, right? We know on average, 25 of the 50 would be heads, but any given 50 coin flips, I could see 26, I could see 30, I could see 21, right? Now, there's some values that are way more likely and less likely. It's way more likely if I flip a coin 50 times, I see 25 heads, than it is if I flip a coin 50 times, it's not very likely for me to see only 2 of them come up heads, right? That'd be very, astronomically low probability. So in order for us to have this binomial, we need that when we run these n number of trials, we can either see a success or a failure. In my coin flip example, heads and tails, right? Or whatever I'm looking for is usually what we're kind of thinking about as our success, and then not seeing that occur would be our failure, right? If I'm interested in seeing how many times heads comes up, success would be seeing heads come up on flipping a coin, and my failure would be tails. And we'll do a couple other examples where we'll see different examples of success, failure, kind of what my 2 different outcomes. But essentially the outcome is binary, right? It's 1 or 0. It's only 2 different possible outcomes. We also have to have that the probability of success across every single trial is the same, right? So when I flip a coin, each time the probability it comes up heads is 0.5, right? We'll look at another example here, and we'll think about how the probability of success in different examples would have to remain the same as well. So if I'm running the exact same experiment, the probability that I see whatever I've defined as a success should be the same across any given trial, right? Any one trial will all have the same probability. And we also have to have that the trials are independent. So if I get a heads on the first coin flip, it doesn't impact the probability that I see a heads on the second coin flip. If that's the case, we've got something that fits our binomial distribution definition, right? So once we kind of have this set up, what we might be interested in is how many successes do I see out of these n trials? If I flip a coin 100 times, what's the probability it only comes up heads 30 times, right? Probably relatively low because we know the average should be about 50, but you know, it's hard to kind of say exactly what that probability would be. So we actually have a function. If the example fits the binomial criteria, we have a function that would give us the probability of any number of successes that we're interested in. Okay? So this probability, right, is going to come from a probability mass function for a specific discrete random variable, which is binomial. Right? So this probability will be the probability that we see X number of successes out of N number of trials. Right? And it looks a little messy, right? So I'll try to describe this formula. We'll make sure that we understand everything that's going on in it. It's a little bit more complicated maybe than things we've used already, but really it's not too tough. Okay? So here we know what. Let's just identify the pieces of this formula. So X is the number of successes you're interested in. So if I'm flipping a coin 100 times and I want to know what's the probability that exactly 50 of them come up heads, my X would be 50, and my number of trials there would be 100. Now the probability of success is the probability of success on any one trial. So if I'm flipping a coin, that probability is just 0.5. Right? So N is the number of trials, X is the number of successes you're interested in finding out of those N trials, and P is the probability of success on one trial. Right? What you're trying to find is the probability of seeing X number of successes, maybe 50 successes out of those 100 trials. Okay? So we don't know what that is, but we know the probability in any one trial is 0.5 for flipping a coin. Okay? Now here we just got the probability of that success raised to the power of the number of successes times 1 minus that probability of success to the raised to the power of the number of trials minus the number of successes. So what I would always suggest is once you plug these numbers in, like don't keep this in parentheses. Like if this is 150, just do the math, 100 minus 50, and write the 50 down, right? There's no reason to keep all the parentheses if you can do the math, that part of the formula, if you can do the math in your head. Now the one thing we probably haven't seen maybe is this factorial. So what a factorial means is, and I think I have a more exact definition, but I think the easiest way I always describe it is, if I've got something like 5 factorial, that's just 5 times 4 times 3 times 2 times 1. If I have 10 factorial, that's 10 times 9 times 8, all the way down to 1. Right? So let me blow this up a little bit. See this. All right. So the kind of the technical definition is you start at whatever the number is, times that number minus 1, times that number minus 2. But logically, you just take the number that's in front of the factorial, in front of that exclamation sign, and you multiply down to 1. Right? So if it's 100 factorial, 100 times 99 times 98 times 97, all the way down to 1. Right? That's all the factorial means there for us. Okay? So we'll get some practice using some actual numbers with this, but just to make sure, are there any questions or understanding any other part of this formula? Okay? Once we have numbers plugged in there, this should be stuff, math that you've already seen before. You're just taking things to a power. The factorial is a little bit different, and we'll talk about some ways that we can make that a little bit easier in certain examples. But you should have that on your calculator. Usually if you have like a TI 83, 84, you hit second math, and then you like go over, there's like a PRB or a probability. If you have like a kind of not as advanced of a calculator, usually there is like a PRB button on there or a math button that allows you to then find probability things, and there's an the exclamation point there for the factorial. If you're having problems on your calculator finding that, email me or set a Zoom meeting up or a time to stop by my office, because you will want to know where that button is on your calculator prior to the exam. okay? So like I said, on that TI 8384, I think is it second, you've got one, is it second math? Math, okay, there's no second that. So math, and then you go over to probability, right? So on the like, some of the not as advanced calculators, I think you have to hit second math or second, and usually then the probability will be under that. But if you can't find it, let me know. I haven't not been able to find one yet, unless, you know, you've just got one of those like dollar store ones. I don't think that's built into that, right? But on a financial calculator, anything like that, I should be able to help you find where that factorial button is. Okay, just some things to note. 0 factorial is kind of a weird one. It's actually equal to 1, right? So if we have 0 factorial, you can think that that's just gonna be 1. Also, anything to the 0 power, just as a reminder here, let's say I took something to the 0 power, anything to the 0 power is also what? Just 1, right? So 0 factorial and anything to the 0 power, that's just 1. Okay? And we'll see an example of that. I don't know about today, but for sure next class. So let's try to walk through a coin flip example, and then we'll start next class working through some more complicated ones. So let's say we have a coin, but now we know it's not a fair coin, it's bias, right? So if I flip this coin 10 times, right, what's the probability that exactly 4 of them come up heads, right? Well, this biased coin has the probability that it comes up heads. It's not as 0.5, but it's biased, so it's 0.4. So here, what would the number of trials be? Well, we're flipping the coin 10 times. The probability it comes up heads, or we see a success on any one trial, is 0.4, so that's our P. And then the number of successes we're interested in finding the probability of, we want to know what's the probability that we see 4 out of these 10. So our X would be 4. So N is 10, X is 4, our probability of success there is 0.4. From here, it's really just a matter of plugging things into this formula, right? We've got 3 components. Everywhere there's an N, we plug in a 10. Everywhere there's an X, a 4. And everywhere there's a P, 0.4, right? So we go ahead and do that. And I'll get this over here. If I go ahead and do that, right? Now it's just a matter of being able to enter this into my calculator, right? Now, how I would usually do this is I would break it down into components. So I would do this part first, like 10 minus 4, just write a 6 in there. There's no reason to keep a bunch of parentheses in there. 1 minus 0.4 is 0.6, so take 0.6 to the 6th power, multiply that by 0.4 to the 4th power, write down that number, and then now figure out what this guy is. Okay? So if you have that factorial button in your calculator, and you found it, you can just enter in 10 factorial divided by 4 factorial times, what, 10 minus 4 is 6, so 6 factorial. Now be careful as you're doing this in your calculator, right? You need to make sure that you're dividing by 4 factorial times 6 factorial, not divide by 4 factorial and then multiply by 6 factorial, right? You need to make sure you're doing what's in that denominator first, okay? Now I'll show you a slightly easier way to kind of deal with this. And it doesn't matter as much for these small numbers, but I'll show you an example of how you can think about it would matter if we had larger numbers. So let's say I'll use those exact values. So I have 10 factorial over 4 factorial, 10 minus 4 factorial. Well, I could rewrite this as 10 times 9 times 8 times 7 times 6 times 5, etc. And then what's this? So this would be 4 times 3 times 2 times 1. Right, that's just 4 factorial. And then 6 factorial would be 6 times 5 times 4, all the way down to 1. But notice, everything past 6 is going to cancel here. And so now if I don't want to use the factorial button in my calculator, all I have to do is 10 times 9 times 8 times 7, divide that by 4 times 3 times 2 times 1. Right? So if I write out those factorials, sometimes it makes my life a little bit easier. In fact, let's say instead I had, I don't know, 100 factorial, 2 factorial, 100 minus 2. Right? What happens if you try to put 100 factorial into your calculator? Yeah, it's going to come up as an error. It's going to say, I can't do this, right? In fact, I don't even know how Excel can do it, right? At some point, it's just too large of a number, right? That's 100 times 99 times 98 starts to add up pretty quick. But if I rewrite this, right, this is 100 times 99 times 98 all the way down to 1. And I'm dividing that by 2 times 1, 2 factorial. And then this is 98 factorial, so times 98 times 97 all the way down to 1. Well, notice everything past 98 would cancel. This is as simple as 100 times 99 divided by 2 times 1. Right? So on the exam, sometimes what I might do is give you one where I know this is going to be really hard or your calculator can't handle it. But if you can write this out, here's one of those examples where if I have a piece of equipment that's supposed to make my life easier, sometimes I have to be smarter than the equipment, right? If there's limitations on it, because it's trying to do it in a way that gets these astronomical numbers, it's not going to be able to do it. But if we just think about, oh, there's a lot of things that would cancel here, this simplifies down to something that I can do very easily, right? So we might run into a few examples like that, but for this one, your calculator, no matter what you're using, should be able to handle 10 and 4 factorial and 6 factorial. Okay? So we get about 0.25, right? And so that kind of makes sense. I mean, if we think about if I flip a coin 10 times and it's supposed to, the probability on any one coin flip, it's 0.4 that it comes up heads. About on average, we should see 4 of the 10 come up heads. Well, on any 10 coin flips, we could see 5 come up, we could see 6, we could see 3, but kind of the most likely outcome is going to be seeing that 4, right? And we'll talk a little bit more about why that would be the most likely. It kind of seems intuitive, but there's an actual rule behind why it would be the most likely. And then we'll talk about the probabilities of kind of different values for this example, finding the probability that's greater than or equal to 4 coin flips or something like that. So we'll go through more binomial examples next class. We should finish up binomials on Wednesday. We'll start talking about the second discrete random variable that we're interested in, which is the Poisson. I don't think we'll completely get it done. I'll probably do a few more examples to start Friday's class about that Poisson, and then we'll kind of start doing some review. Okay? Any questions for me before we get out of here? All right. I will see everybody was here again on Wednesday if you want to show up.